Bismillah ar-Rahman ar-Rahim. Today we have a very nice technique to integrate rational functions. How to integrate rational functions? We have very nice technique called integration by partial fraction. So what does it mean, integration by partial fraction? What does it mean, partial fraction technique? Here is the idea first. We have the idea is how to write or rewrite actually a rational function where this is polynomial and this is polynomial. Of course, the denominator is not equal to 0. So if you have polynomial over polynomial, how to rewrite it as a sum of simpler fraction? Let us explain this one by the following exercise. What does it mean, partial fraction? For example, here if you have 5x minus 3 divided by x squared minus 2x minus 3. You can show that this is equal to 2 over x plus 1 plus 3 over x minus 3. Now, let us look for the left hand side and the right hand side. If someone asks me to integrate this, it seems this is not as straightforward. But if I will be able to rewrite the fraction here into the sum of these two fractions, each of which is easy to be integrated. Now, the process of moving from this side to this side, from one single fraction into sum of fractions, is called partial fraction decomposition. Partial fraction decomposition. So we are decomposing a single fraction into what? Into sum of fractions. Each one of them is part of the single fraction, so we call it partial fraction. What is the idea now? The idea is how to move in this section, is how to do this, how to rewrite this, how to move from the left hand side to the right hand side. So what we need to do, we will make some assumptions, then we will have a procedure to rewrite a single fraction as sum of fractions. Then instead of integrating the single fraction, which is p of x over q of x, we will integrate the sum of fractions we have. This is the main idea of what we call partial fraction technique. How to do this? We will see it in the following point. Now, how to apply this procedure? How to rewrite a single fraction into sum of fractions? Before we go to that point, let us make some assumptions. Let us assume we have a function which is p of x over q of x. As we said before, that this is polynomial not equal to 0. This is another polynomial. We will assume that the degree of the denominator, degree of q of x, is larger than the degree of p of x. So the degree of the denominator is greater than the degree of p of x. But someone will say, this is not always the case. Yes, it is not always the case. And if not, if we have the degree of the numerator is greater than or equal to the degree of the denominator, what do you need to do? We will use the long division first to simplify. Okay, what happened if we have the degree of the numerator is larger? We will explain this one in the first exercise we have. So this exercise says, evaluate or find the integral of this, which is x cubed plus x, all divided by x minus 1 dx. So before we go to the procedure of partial fraction, we need always to make sure that the degree of the denominator is larger. In this case, it is not the case. We have here the degree is 1, the degree is 3. So before we go to the partial fraction technique, we need to simplify the expression first. How to simplify it? We will simplify by using long division in general, or in this case, we can also use the scientific division if we like. Okay, if we are trying to use the long division, then this is the thing we need to do. As usual, we need to have the x cubed here, the numerator, plus I will write 0x squared just to organize my work, plus x. Okay, that is x cubed plus x we have here. And the divisor here we have x minus 1. Then I start the process here to divide, to simplify. X cubed divided by x, that will give me x squared. X squared by x, that is x cubed. And x squared by minus 1 is minus x squared. Okay, that's exactly what we have. Then what you need to do is just to switch the signs. So this is minus, this will be plus, and add. This will be cancelled out. What do we have here is just x squared plus what? Plus x. Still the degree is larger, so we need to divide. So x squared divided by x, that is plus x. Okay, x by x, that will give me x squared. X by minus 1, that is minus x. Then again, I switch the signs and I add, so I get what? 2x. Still, the degree here is 1, the degree here is 1, so I can continue dividing. So 2x divided by x, that will give me plus 2, okay? 2 times x, that is 2x. 2 times minus 1, that is minus 2. Again, you need to switch the signs. This is plus, so the final will be 2. Now we reach the last one is a constant, so it has a degree less than the divisor. So we stop here, and then we rewrite the fraction as this. We just rewrite it like x cubed plus x divided by x minus 1. Now after simplification, this is equal to what? This is equal to the quotient, which is x squared plus x plus 2. This is the quotient, okay? Plus the remainder, which is 2 divided by the divisor, which is x minus 1. Now, instead of integrating this, I will integrate the right-hand side, which is easier. So what will be the next step now? Our integral, which is the integral of x cubed plus x divided by x minus 1 dx, this will be exactly equal to what? It is the integral of the right-hand side, which is x squared plus x plus 2 plus 2 over x minus 1. Of course, I am integrating with respect to x the whole thing here. Fine. What is the last step? Now, from the previous discussion we made, the integral here is so simple. This is x cubed over 3 plus x squared over 2 plus 2x plus what? 2 ln of absolute value of x minus 1. And I need to add a constant of integration plus c. So, whenever we have a case where the numerator has a degree greater than or equal to the denominator, I will use the long division to simplify first. Then I apply the what we call partial fraction technique that will be explained in the following point. Now, let us assume always this is possible, that the degree of Q is greater than degree of P. What is the next point we need to think about here? Now, all our work will depend on the shape of Q of x. We know that any polynomial with real coefficients can be factored out into what? Product of linear factors, quadratic factors. Combination of this. Either linear factors all the way or linears together with what? Quadratic irreducible factors. So depending now on the shape of Q of x, after factoring, we will classify the partial fraction decomposition case. Okay, so let us look for Q of x and classify the cases we have. I will say case number 1 will be if this denominator Q of x is factored out into product of linear factors that are distinct. None of them is repeated. Sometimes we have the factorization will end up with Q of x that is written as product of linear factors, yes, but some of them are repeated. You may end up with Q of x is factored out into product of non-linear factors. The last one, non-linear factors and repeated. Let me just give some examples here of the cases we have, and then we go to explain the procedure of partial fraction. Okay, let me just give a specific exercise. For example, if Q of x is, let us say, x squared minus 1, simply. You can see easily this is equal to what? X minus 1 times x plus 1. So what do we have in this case? We have a polynomial that is factored out into two factors which are not the same, so distinct linear factors, each of which is a polynomial of degree 1. Good. But if Q of x, for example, it has something like x squared minus 1 all squared, for example. Then what is the factorization of this? It will be x minus 1 all squared, x plus 1 all squared. So these are linear factors, yes, but with a kind of repetition we have, with multiplicity of this. Okay, you may have Q of x, let us write it in factored form, like, for example, if you just have x cubed minus 1, for instance. What will be the factorization? It will be x minus 1 times x squared plus x plus 1. Now you can see now this is linear, but this is not linear. This is not a linear factor. This is called prime factor. You cannot factor it out over reals. This is not factorable over reals. So we said this polynomial is a product of linear factor together with non-linear factor. Similarly, you may end up with polynomial form, let us say x minus 1 times, let us say x squared plus 1 all cubed. So in this case, we say we have polynomial that is written as the factorization of linear with non-linear and repeated. So we count, now we have one case, a second case we have linear and repeated, we have a third case where we have non-linear factor not repeated, and we have fourth case where we have non-linear factor and repeated. Now the next step will be, in each case, how to decompose the fraction. So we will consider now 4 cases. I will start now case number 1, where we have distinct linear factors in the factorization of q of x. Now let us come and treat these cases. The first one of them says, okay, we have p of x over q of x. We assume now q of x is a product of distinct linear factors. What do you mean by this? Distinct linear factors. You can see these are linears. All of these, a1x plus b1, a2x plus b2, etc. These are linear factors. None of them is repeated. So we have 2 things now. First, what is the form of the partial fraction? And then how to calculate the parameters there. First one, the partial fraction decomposition says that always, whenever we have this case, then always it is possible to rewrite the fraction as follows. You have a constant here, call it, for example, a1 divided by the first fraction a1x plus b1, plus another constant, we call it a2 divided by the second factor here, which is a2x plus b2. Okay, so I need constant over the first factor plus another constant over the second factor, plus you do the same until you reach the last one. So we have n of them, so we need another constant, we call it an divided by anx plus bn. As we are assuming now we have polynomial of degree n in the denominator, okay, and it is written as product of linear factors. None of them is repeated. So the partial fraction decomposition form will be as follows. Now, the next one, how to obtain these parameters. We need to find a1, we need to find a2, we need to determine an, all of them. And then we start integrating. So the idea is to rewrite such type of fractions into sum of fractions. So we call it partial fraction decomposition. Partial fraction decomposition. How to do this procedure? Meaning, how to calculate or how to decompose a singular fraction of this type, where we have the denominator is written as the product of linear factors. None of them is repeated. How to decompose it practically? That will be explained in the exercise now. So this is the decomposition form. Now let us apply it in a concrete exercise. I will start with a simple one. For instance, I can start with a very simple one. Example number 1 is so simple, that is, it says find the following integral. Integral of, let us say 1 over, just for simplicity, to explain this idea, x squared minus 1 dx. Okay, very simple exercise. 1 over x squared minus 1 dx. Okay, how to integrate such type of functions? Let us see our assumption first. Before we go to the procedure here, I need to make sure that the degree of the denominator is larger than the degree of the numerator, which is hold true here. Okay, fine. After that, what I need to do, I need to rewrite 1 over x squared minus 1. I need to first factor out the denominator. So this is equal to, I write it like 1 over, what is this? X squared minus 1. Difference of 2 squares. So this is x minus 1 times what? X plus 1. Fine. Interesting. The partial fraction form here, the partial fraction decomposition form says, always you can rewrite this as you can rewrite it as a constant, let's call it a, divided by the first factor here, that is x minus 1, plus another constant b divided by the second factor here, x plus 1. What is your duty now, or our duty actually, is to determine what is a, what is b. Then integrating this will be the same as integrating the right hand side, which is much more easier than integrating the left hand side. Now let us see how to get a and b. How to determine these values a and b. Okay, that is so simple. Okay, let's see it now. What we need to do as a first step. Now after writing everything in this form here we have, what we need to do in the second step, just multiply by the LCD, multiply by x minus 1, x plus 1, both sides of the equation. What do we get? We get 1 equal to, when you multiply here, you get a times what? X plus 1. Why? Because x minus 1 will be deleted, right? Plus the second one, we have b times what? X minus 1. Okay, simply this is the second step. So the first step, after checking that the degree of the numerator is less, we write the partial fraction decomposition form. Second step, I multiply by the LCD to get this form. The third step now, you have the two options. Either you compare two polynomials by their coefficients, or you substitute points because you have two polynomials are the same. Two polynomials are the same if you have the same degree, the same coefficients. Okay? Or you can say it in other words, they agree at each single point in the domain. So what do we have here? I will do it by, let us say, if you like, method 1. So method 1 will be what? Method 1, it means we are comparing coefficients of both sides of the equation. Now let me start with the coefficient of, what is this? This is polynomial of degree 1. So I will say, what is the coefficient of x here? What is the coefficient of x in the right hand side? In the right hand side, the coefficient of x will be a, which is a times x, plus what? Plus b, isn't it? And the coefficient of x in the left hand side is 0. So we get one equation. Another one. What is the constant term? Constant term. What is the constant term here? The constant term is gained by multiplying a by 1. So that is a plus minus b. So it's minus b. Now what is the constant term in the left hand side? The constant term is just what? 1. So we end up with what? We end up with two equations, two unknowns. We solve them. How to solve them? Add them together. What do you get? We get 2a is equal to 1. So this implies a is equal to 1 over 2. So this is one thing we need to find. Now, using the first one or the second one, any one of these two equations, for example, the first equation, if we substitute a equal to 1/2, we will get b equal to what? b is equal to minus 1/2. What does it mean now? After getting a and b. Going back to the question, we need to integrate 1 over x squared minus 1, which cannot be done directly, but after decomposing now, what we have at the end, we get the value of a, we get the value of b, so we can rewrite 1 over x squared minus 1 as, what is a? A is 1/2, so this is 1/2, and this is what? Minus 1/2, and then we get the answer. Okay. So what is next now? The next step will be, we just rewrite the equation, which is 1 over, look, we have x squared minus 1, okay, dx, and this is equal to the integral of, after decomposing now, we have the value of a is 1/2, so we can take, this is 1/2, and what do we have downstairs? We have x minus 1, then I have minus 1/2 divided by x plus 1, and I need to integrate this one with respect to x. Okay. You see now the beauty of partial fraction. We start with a single fraction that cannot be integrated. After decomposing, we end up with fractions. Each one of them is simple to be integrated. So what is the next or the last step here? We have, I will take the 1/2 if you allow me as a common factor. Then I will find the answer to be ln of course, this is absolute value of x minus 1 minus ln of absolute value of x plus 1. All of this plus a constant of integration c. Or, if you like, you can rewrite this one as 1 over 2 ln of absolute value x minus 1 all over x plus 1 all plus constant of integration c. Okay. This is very interesting now. So what is next? Let us do it in general then. What happened if this is x squared minus a squared, where a is not equal to 0? So we can use this technique now to derive formulas also. That will be our next exercise, a modification of the first one. Okay, let's talk about the following exercise now. Let us try to see how partial fraction will be used to derive formulas. And the question here simply will be the following. Okay, what is the question? The question will be like this. So this is our next exercise or example. Says find the integral of 1 over what? X squared minus a squared dx. I'm assuming here a is not 0. Why? Because if it were 0, this is simple to be integrated. If we just remove this, it is 1 over x squared. That is so simple to be integrated. So we are interested in the question where a is not equal to 0. Okay, which is a generalization of what we did in the first part actually. Fine. As usual, we check that the numerator has a degree less than the denominator, which is there. So what I need to do, I just write the integrand as x minus a multiplied by x plus a. Okay. Before I move and continue this question, let me go back to the previous one we have and illustrate another way to get a and b. Okay? How to get it in another, let's say, second method if you like, or to get a and b by another method here. Let's call it method number 2. Method number 2 for the first exercise. Sorry for this. Okay. We said here we can compare coefficients to get the answer. Another way, alternative way to get a and b, you can substitute points in the left-hand side and the right-hand side. Try to choose the points in a clever way. Meaning, when you come to substitute points, try to choose the points to be the zeros of these. Okay? What is the 0 of x plus 1, for example? Minus 1. So you can choose 2 points. You can choose x equal to 1. If x equal to 1, if x equal to 1, what do we get? If x equal to 1, this will be 0. This will be 1 plus 1 times a. That is what? That is 2a equal to 1. So this implies a is equal to 1/2. Now, if you choose x equal to minus 1, then what do we get? This would be 0. This will be minus 1 minus 1. That is minus 2 times b. That is minus 2b is equal to 1. You end up with b is equal to minus 1/2, which is the same as what we did in the previous technique. Okay, fine. This is just a comment about the second method to find the parameters a and b. Let's come back to the question we are explaining now or discussing now. This is equal to what? According to the partial fraction decomposition form, says this is equal to a constant a divided by x minus a plus another constant b divided by x plus a. This is what we have. Multiplying by the LCD, what do you get here is 1 equal to, it is capital A multiplied by x plus a. That's the first one. Plus the second one, b times x minus a. Fine, interesting. You look here, 1 equal to a times x plus a plus b times x minus a. What is our duty now is to find or to determine capital A and capital B. So let us try to do that by either using the first technique we did or using the second technique we did. Okay. So we are still in case number 1 where we have distinct linear factors in the denominator. Fine. How to get A and how to get B. How to determine A, how to determine B. That's our challenge now. I will choose points for this case. So I will choose x equal to A, for example. If x equal to A, if you substitute x equal to A in the right hand side as well as the left hand side, what do you get? If we substitute A, this will be 0. And this will be what? A plus A. That is 2A. So what do we get is 2 small a, capital A is equal to 1. So this implies capital A is 1 over 2A. Okay. How to get the value of P? How to get the parameter P? I will substitute x equal to minus A. Okay. Other choices for x are also possible, but these are recommended choices because it will simplify the calculations. If you choose x equal to minus A, for instance, this would be 0. Minus A, that is minus 2A. So what do we get is minus 2A times capital B is equal to 1. So B will be equal to what? Minus 1 over how much? Over 20. That's exactly the value of A capital and B capital. Now, let us go back and substitute here. So this implies now the integral of 1 over x squared minus a squared dx is nothing but the integral of, now we just substitute in the partial fraction. So we get the value of a, which is 1 over 2a. This is 1 over 2 small a divided by whatever we get there, x minus a, minus 1 over 2a divided by x plus a. All of this supposed to be integrated with respect to x. Now, as what we did before, what you need to do is just to take 1 over 2a. So it is simple now to show that this is equal to 1 over 2a. Then do the same as example number 1. You get here what? X minus a over x plus a, and all of this plus constant of integration. You see, we have a question that after decomposing, we get simpler integrals that can give me the answer. So this is, as application for the partial fraction, we can now derive the formulas for such type of integrals that can be gained directly now. If you apply for the example, in the first example we did, if you remember, this is our example we had before. So our a here is equal to 1. If a, so this will be 1/2. This is x minus 1. This is x plus 1, which is exactly what we have in the final answer. So you can see now the beauty of the first case. We have partial fraction. I will show you another exercise of the first case where we have the denominator is factored out into product of linear factors. Okay. Now let us see more about this case we have. The first case. Remember, we have the first case, the denominator is factored out into linear factors, none of which is repeated. We have distinct linear factors. The exercise here says, evaluate x squared plus 2x minus 1 divided by this. I always remind you, always check that the degree of the numerator is less than the degree of the denominator. Before you proceed writing the decomposition form, make sure that this is hold true. Okay, it is there here. Okay, we have no problem. So what should we do then? As a first step, I need to take my integrand. I need to take my integrand x squared plus 2x minus 1, and I start factoring the denominator, because our case here is depending on the shape of the denominator. So as the first step, I will take here x common factor. What do we get is x times what? That will be 2x squared, okay, plus 3x, and finally we have minus 2. Fine. Then I need to go to the quadratic expression I have here and also factor it out. One way to do it is to do it this way. You have 2x squared. This is factored out into 2x times x. I need it to be plus 3 here, so this is supposed to be 2 times minus 1. So that we have 4x minus x is 3x. So this is actually is equal to what? This is equal to, okay, I copied the same thing before x squared plus 2x minus 1. The factorization form will be now x times whatever we have here, 2x minus 1, for example, and x plus 2. Now, look for the denominator. The denominator clearly is written as product of factors. All of them are linear, first order, and none of them is repeated. This is x, 2x minus 1, x plus 2, so all of them are linear and no repetition. So we are at the first case where we have distinct linear factors. Now let us come to the partial fraction decomposition form. The partial fraction says that always you can write x squared plus 2x minus 1 all over x times 2x minus 1 times x plus 2. You can always rewrite this one as follows. You need a constant, you call it a, for example, all divided by the first factor, that is x, plus another constant for the second factor, you call it b, for example, and then divided by 2x minus 1 plus a third one. So if you allow me, I'll just take some space here. So plus the third one, you may use c, you can use d, whatever you like. I will use d here. I will save the letter c for constant of integration. Doesn't make a difference here. Use any letter you like. Okay. What is the challenge in the next step now? The challenge is how to get a, how to get b, and how to get d. These parameters. And we explained this one before. I will explain it again in this exercise by the two methods we have. And then you see which one is easier, you can use it. Okay. In both of them, I need to multiply by the LCD. So that is x squared plus 2x minus 1. I will multiply both sides by this expression, which is x times 2x minus 1 times x plus 2. What do we get in the right-hand side? We will get here a times what? X will be deleted, so we have 2x minus 1 times x plus 2. That's one thing here. Okay. The second factor I have b times what? Now this will be deleted, so I have x times x plus 2. So it is bx times x plus 2. Fine. Finally, I have to multiply the last term by the same thing here, so I get plus, that is d times, now 2x minus 1 will be deleted, so I have x plus, that is something mistaken here. I have, instead of 2x minus 1, this is supposed to be what? This is supposed to be x plus 2. Made a mistake here. Yes, we'll modify it. Here it is a over x plus b over 2x minus 1 plus d over x plus 2. That's the partial fraction decomposition form. Now let's come to the last one. X plus 2 will be cancelled out. So we have x multiplied by the second one here. We have again, I need to make space here. So this is what we have here is dx times what? 2x minus 1. 2x minus 1. Okay, fine. Interesting. Let's do it this way. Now, how to get these constants, a, b, and d? I will do it in two ways. The first one, method number 1 will be used comparison between the two polynomials in terms of coefficients. We have the coefficient should be the same. So I will start comparing the coefficient of x squared. Okay, what is the coefficient of x squared in both sides of this equation? The coefficient of x squared, you can see here, 2x times x will give me x squared, so it is 2 times a, that is 2a. Okay? Second one, that is plus b. In the last one, we have 2d plus 2d. Now, what is the coefficient of x squared in the left-hand side? It's equal to 1. So that is equal to 1. We get one equation now. Second equation will be coefficient of x. What is the coefficient of x here? The coefficient of x, you can see here, x will be again, you can say 2 times 2, that is 4, minus 1, that is 3, times a, that is 3a. Okay? Coefficient of x here, this is just plus 2b. And finally, the coefficient of x here is came from here, so this is minus what? Minus d is equal to. What is the coefficient of x here? It's equal to 2. Fine. Last one, constant term. constant term. What is the constant term here? The constant term will be gained by, if you multiply minus 1 by 2, so that is minus 2a, okay? There is no constant term here and there is no constant term here. So it means minus 2a is the only part we have in the right hand side. What about the left hand side? What is the constant term here? The constant term here is minus 1. So we end up with what? 3 equations. And we have 3 unknowns. Easy to be solved. So what can we gain from the last one, for example? Okay. From the last one we have a is equal to 1/2. That's one thing we have in the last equation. Now let's come back and substitute in the first and the second equation. What do we get? Substituting here. In equation number 1, equation number 2, 2 times 1/2, that will be 1. 1 minus 1 will be 0. So what do we get is b plus 2d is equal to 0. This is what we end up with here. Okay? If we substitute a equal to 1/2 in the last one here, this will be 3 over 2. 3 over 2. 2 minus 3 over 2, that's equal to what? That's equal to 1/2. So what do we get is 2b, okay? 2b minus d is equal to 2 minus 3 over 2, which is what we said it is equal to 1/2. Now we solve this system of 2 equations, 2 unknowns to get b and d. What I will do here, if you like, I will multiply by 2. So what do we get is the following. I get b plus 2d is equal to 0. I'm trying to use elimination method here. So this is 4b minus 2d is equal to 1. I'm just multiplying by 2 in the second equation. Now I add them, what do we get? This will be 0. So I have 5b is equal to 1. So this implies b is equal to 1 over 5. That is the second parameter we need to find. Okay. Now b equal to 1 over 5. From this equation, what do we get? We get, or from that one, it's up to you. You get d to be equal to what? D is equal to minus b over 2. So that is minus 1 over 10. 1 over 5 divided by minus 2. So that will give me the parameter what? D. Okay. First method, we compare coefficients, we add up with equations, we solve equations to get the answer. Alternatively, what do we need to do if we have such a case? We can do it by second method if you like. It is not a second method, rather it is just a second representation of the technique we are doing here. So how to get A, B, D alternatively? You can do the same, reach up to this step. So I will copy this line again. I will have it here, x squared plus 2x minus 1 equal to A times what? 2x minus 1 as it is written before times x plus 2. I'm trying to copy the same thing here. Plus, what is that? B times x times what? X plus 2. Okay, and then finally we have plus dx times 2x minus 1. That's exactly what we had in the first or the second line here. Okay, how to get A, B, and D alternatively? Choose some specific points, key points. Use key points. So what do we need to choose here? We need to choose the points x equal to, look, 3 points of interest here. X equal to 0, the 0 of x, of this, x equal to 1/2, and x equal to minus 2. So if you substitute 0, what do you get? You can figure out that this will be 0, this will be 0. So what do we have? 0 plus 2 is 2. 0 minus 1 is minus 1. 2 times minus 1 is what? Minus 2. So it is minus 2a is equal to. If you substitute 0 here, what do you get? You get minus 1. So directly you can get a is equal to what? 1/2. So you get the value of a as it is appearing here. A is equal to 1/2. Same. Second point of interest. If you substitute x equal to 1/2. Why I chose 1/2? Because it is the 0 of the second factor we have here, 2x minus 1. The 0 of it is 1/2. So x equal to 1/2, this will be what? 0. Why? Because this will be 1 minus 1. And this will be 0. What it remains only this. So what do we have? If you substitute 1/2, 1/2 plus 2, look, we have b times 1/2 times 1/2 plus 2, that is 5 over 2. When you multiply, you get what? You get 5 over 4 times what? B equal to. This is the substitution in the right hand side. What about the left hand side? If we substitute 1/2 in the left hand side, this will be what? This will be 1 over 4 plus 1 minus 1, because 2 times 1/2 is 1 minus 1. So what do we have here is 1 over 4. Multiplying by 4 will cancel this. So what do we have? This implies B is equal to 1 over 5. That's exactly what we found by the first technique. B equal to 1 over 5. Finally, we need to determine D. To determine D, I come to this factor and substitute minus 2. So I will choose the point x equal to minus 2. I'm choosing this as a 0 of the last factor we have. If you substitute minus 2, this will be 0. This will be 0. So what do we have here? We have minus 2 times 2, that's minus 4, minus 1, that's minus 5, times minus 2, that is equal to 10. So what do we get is 10D equal to. Now if you substitute minus 2 in the left hand side, this will be 4, this will be minus 4. So this will be what? 0, right? So what do we have is minus 1. The answer is D equal to minus 1 over 10. Okay, fine. We get the same answer regardless of the way we did. We get minus 1 over 10, 1 over 5, 1/2. Minus 1 over 10, 1 over 5, 1/2. Now you have the freedom to use the first method or the second method to determine the constants. Okay, after determining these constants, how to get the answer? Let us finish this exercise by integrating now the function. To integrate this function we have here now, it's exactly equal to the integral of, now I need to come to the partial fraction and replace A, B, and D. Substitute for these values. What do we get? We get 1/2 divided by x. What is B? B is 1 over 5. So that is plus 1 over 5, okay, divided by 2x minus 1. Finally, I have to substitute for D. D is 1 over 10 divided by what? X plus 2. You can see now we started with a little bit complicated function. After decomposing, we end up with simple integrals, simple fractions, simpler fractions. We can integrate each one of them easily. Okay, to get the final answer, quickly we have the following answer. The final answer will be just this is equal to, you can see clearly that this is equal to, our integral is equal to 1/2 ln of absolute value of x. That's the first one. You can take the constant out and integrate. For the second term here, we need the derivative of this. The derivative of this is 2, so we multiply by 2 and divide by 2. So that will give me plus 1 over 10, because I need to multiply by 2 and divide by 2. And that is logarithm of absolute value again, 2x minus 1. Okay? And finally, I have the last one is 1 over 10 ln of absolute value of x plus 2. And that is what we have here is, I substitute for D by 1 over 10. It's supposed to be, this is supposed to be minus 1 over 10 because D is minus 1 over 10. Okay? So this is supposed to be what? This is supposed to be minus of 1 over 10 ln of x plus 2. And finally, I need to add a constant of integration. Actually, we copied this one wrongly in the substitution, but this is supposed to be minus 1 over 10, not 1 over 10. So that's the final answer. You can see the beauty now of partial fraction. Still, we are at the first case where we have what? Where we have the denominator, I'm repeating this. If we have the denominator is written as product of linear factors. Okay, let's see the last exercise in the first case. The last exercise in the first case is the following. What I need to clarify in this exercise, just to remind you, it's something that need not to be calculation. Okay, let's see the exercise first, then I will comment on this only and show you how to find the answer. And that will be the last exercise we have for the first case, and then we move to another case of interest. Now, we don't forget if someone asks us to evaluate or to find the integral of what? We have here 2x cubed minus 4x squared, okay, minus x minus 3 divided by x squared minus 2x minus 3 dx. Now, a common mistake will be the following. Maybe someone will say, okay, I will try to factor out the denominator. Fine. He will take x squared minus 2x minus 3 and he will write it like what? X minus 3 times x plus 1, isn't it? This is the factorization. And he will start say that, okay, this is a, polynomial that is written as product of linear factors which are distinct. None of them is repeated. So he will start writing the decomposition form of this to be equal to, okay, I will say this is equal to a divided by x minus 3 plus b divided by x plus 1. And this is totally not correct. Why? Because don't forget our assumption here. Our assumption is the numerator has a degree less than the denominator. If you look at it carefully here, this is x cubed, this is x squared. So this is larger than this. So you cannot say this is the partial fraction decomposition form. So what do you need to do instead then? What you need to do is the following. As before we said, what we need to do is to use long division to simplify first. And if you use long division, this can be written as, this expression will be 2x plus, I'm just commenting in that important remark I need to address here. 5x minus 3 over, of course this is x squared minus 2x minus 3 dx. Now what do we need to do next? This is the first important step that I need you to remember. Then the rest will be just, of course I'm integrating everything here. The rest will be just taking this 5x minus 3 and do the same as what we have. This is x minus 3 times what? X plus 1. And then we need to decompose it. Now we can decompose. Now we can write this one as a all over what? X minus 3 plus another one b over what? X plus 1. And then as before, we need to find a, we need to find b, we substitute, we get the answer. I guess this is a good exercise for you to determine a and determine b. I will give you the values of these quickly here. What is the value of a and what is the value of b? The value of a, which is, it will be 3, this is equal to 3, and b is equal to 2. b is equal to 2. You can justify these calculations. You just multiply by the LCD, do the same procedure as what we had before, then integrate to get the final answer. And that is what we mean by the first case where we have what? We have distinct. Of course, this is not yet complete. It is good exercise for you. The idea I bring this exercise just to address that you need always to make sure that the degree of the numerator is less than the degree of the denominator. In other words, they call it a proper fraction. Okay. What is next? What happened if we have kind of repetition in the factorization of q of x? Or what happened if we have nonlinear factors? This will be done in the next part. Now, after we discuss the first case where the q of x is factored out into linear factors, none of them is repeated. Let's just see the second case. The second case we have for partial fraction, that is if q of x is a product of linear factors, yes, but some of them are repeated. Remember, the first case we have the same, q of x is a product of linear factors, but we said none of them is repeated. We have distinct linear factors. Here we have some of them are repeating. As an example, if you just take q of x to be product of two factors, let us say, one of them is of degree 1, let us say of multiplicity equal to 1, a1x plus b1, so it is not repeated. But the second one here, a2x plus b2, which is linear, yes, but it is of multiplicity equal to m. What will be the form of the partial fraction? So our rational function will be like this, P of x over Q of x. Okay, we set Q of x for the denominator, so this is what we have. We said always that we need to make sure that the degree of P is less than the degree of Q. Assume this is happening here and Q of x has exactly this shape. So what do we have at the end? This will be the case. We have P of x divided by, and we just rewrite Q of x to be A1x plus B1. That is a linear factor of multiplicity equal to 1. Then we multiply by A2x plus whatever we have here, P2 raised to the power m. It means we have a linear factor but with multiplicity equal to m. Now, what is the form of the partial fraction? The form will be like this. For the linear one, you need one constant. We call it, for example, A. So we have A over A1x plus B1. Okay, plus. Now, for the linear factor which is repeated m times, we need m constants. Let us name them, for example, to be the first constant, I call it B1, for example. So it is B1 divided by A2x plus B2. That's the first one. Plus, we need another constant. Let's call it, for example, B2. So it's B2 divided by A2x plus B2. Now we start increasing the power. So this is all squared plus and etc. Until we reach what? Until we reach the last one, that is the m constant. So it is Bm divided by A2x plus B2 all to the power m. So always this is possible. If we have linear factors, some of them are repeated, then always we can decompose the fraction into such type of fractions. So simply if you have multiplicity equal to 1, then you need only one constant. But if you have multiplicity equal to m, you need 1 up to m, that is, we need m constant. You start with the power 1, then to the power 2, to the power 3, to the power 4, until you reach the highest power, which is m. That is the form of the partial fraction if in case we have one polynomial that is factored out into linear, but some of them are repeated. Practically, how to integrate now? Let us take a specific exercise. So our next exercise will be like this. It says, evaluate the following integral. Evaluate the following integral, and this is the integral we have. It is 4x, okay, divided by, and we have here x cubed minus x squared minus x plus 1, and this is dx. Before we start, as usual, we need to make sure that this is proper fraction, meaning we have the degree of the numerator is less than the degree of the denominator. It is there. Now, to move, we need to classify the case. Okay, what type of denominator we have? We need to factor it and see. So we start now factoring the denominator. So I will take this 4x divided by x cubed minus x squared minus x plus 1 and try to factor out the denominator. Clearly we have here 4 terms, so factoring by grouping is recommended. So what I will do here, I will take from the first 2 terms, I will take x squared common factor. Now what do we have if you take x squared common factor? You have x minus 1, okay? And then you have a minus sign common factor from here. So this is minus sign, and then again you have x minus 1. Okay, and then of course this is just 4x. X minus 1 now is a common factor. We can take it out. So this is equal to 4x divided by, now if you take x minus 1 common factor, what is left is x squared minus 1. Fine. Now x squared minus 1 is difference of 2 squares. So what do we get at the end? This is exactly equal to, look, 4x divided by, this will give me x minus 1 times x plus 1. So at the end we have x plus 1 times x minus 1 all squared. Okay, something like this. I'm factoring this one as difference of 2 squared, so I get x minus 1, x plus 1, x minus 1 times x minus 1 will give me x minus 1 squared, and still I have what? X plus 1. Fine. This is the factorization. Now, if we look for the cases we have, now this is a case where we have the denominator is factored out into linear functions, yes? But one of them is repeated in this case. So what will be the form of the partial fraction decomposition? Okay. I come to the function now, 4x divided by whatever we have here, x plus 1 multiplied by x minus 1 all squared. Now, according to the case we have here, what we need to do here is just to write one constant for the first one, that is, I call it a, for example. So it is a over x plus 1 plus, now, for the second factor here, which is a factor of multiplicity equal to 2, I need two constants. So I may call them, for example, b divided by x minus 1 and plus, now I need another constant, so I call it d, for example, divided by x minus 1 all squared. Okay, I save the letter c for the constant of integration. Now, what is left here is to find a, b, and d. To determine a, b, and d, we do the following. We multiply first by the LCD, so what do we get here is 4x equal to. Now, if you multiply by the LCD, what do you get? You get a times, of course, x plus 1 will cancel with x plus 1. You have a times x minus 1 all squared plus. For the second one, I have b times what? X plus 1 multiplied by x minus 1. Why? Because x minus 1 all squared, one of them will be cancelled out, one of them will survive here. Plus the last one is just d times x plus 1. Fine. Now, how to get a, b, and d? We said we have two options. Either we substitute some key points, or we compare coefficients of two sides of the equation. So we have polynomial here, we have polynomial here. Either we compare the coefficients, or we substitute points, then we get the parameters a, b, and d. For me, I will choose to substitute points in this case. So I will choose, for example, here, I will choose first x equal to, I need to get this one, so I will choose first x equal to minus 1. Okay, if I choose x to be equal to minus 1, this term will be 0, and this term will be 0. And this will be what? Minus 1, that is minus 2. Minus 2 squared, that will be 4. So that will give me 4a is equal to, if you substitute minus 1 here, what you get is minus 4. So this implies a is equal to minus 4 divided by 4, that is equal to minus 1. So this is the first parameter we need to find, which is equal to minus 1. A equal to minus 1. What else we can substitute now? I will choose to substitute the second point to be the 0 of this, which is 1. If I substitute 1, what do we get? If I substitute 1, for sure this will be 0. And also this will be 0. But this will be 1 plus 1, that is 2. 2d. So I get 2d is equal to. I substitute 1 in the left-hand side also, so I get 4. So this implies d will be equal to 4 divided by 2, that's equal to 2. Now we get two of them, a and d. Next, what is the next suggestion here? I need to choose another point. Okay, we already used 1 and minus 1. We have the freedom to choose the third point. I will choose it to be 0 to make things easier in calculation, easy in the calculation. Okay, if x equal to 0, what do we get? Substituting 0 here, you get 0 minus 1, square it, you get 1, so that will give me a. Okay? Now, if you substitute 0 here, what do you get is 1 times minus 1, that is minus 1. So that will give me minus b. If you substitute 0 here, you get 0 plus 1, that's 1 times d, so it is plus d. And if we substitute 0 in the left-hand side here, we get 4 times 0, that is equal to what? That's equal to 0. Now, already we had this. We have a and we had d, so we can substitute to get what? To get the value of b. What is b? b is nothing but, and this implies b is equal to, if you take it the other side, you have it a plus d, and simply this will give you what? If you substitute for a by minus 1 and for d by 2, adding them, you have the answer is equal to 1. Okay, so we get the value of b, we get the value of a, we get the value of d. Simply what you need to do is just to go back and substitute here and then do the integration. So our integral now, which is the integral of 4x divided by whatever is there, x cubed minus x squared minus x plus 1 dx. This is exactly equal to the integral of, now after decomposition, we substitute for a is equal to minus 1, so that is minus 1 over x plus 1, that's the first one, plus b, what is b? b is equal to 1, so it is plus 1 over, okay, we have x minus 1, and finally we have plus d, d is equal to 2, so that is 2 divided by x minus 1 all squared. Of course, I need to integrate this with respect to x. Everything here should be integrated with respect to x. So I need to put like brackets like this, or yeah. How to integrate now the new form of the integrand. This is easy to be integrated, this is easy to be, and this is easy to be integrated. This is the beauty of partial fraction. We start with something that we cannot integrate, we decompose it into things that can be integrated easily. What is the final answer? Now this will be equal to, of course this is minus ln of absolute value of x plus 1, straightforward. And that is plus ln of absolute value of x minus 1, okay? And finally, I need this is x minus 1 to the power minus 2, so it is x minus 1 to the power minus 1 over minus 1, or simply it is minus 2 over x minus 1, of course, plus a constant of integration c. Now you can leave it this way, you can rewrite this as ln of absolute value, okay, using the properties of logarithm. This is x minus 1 over x plus 1 all minus 2 over x minus 1 plus a constant c. So this is the idea if we have a repeated linear factor. If you have a repeated linear factor, remember that if we have multiplicity equal to m, then we need 1, 2, up to m, so we need m constant. We start with the power 1, the next one will be 2, until we reach the last one, which is what? The power we have in the fraction here. So this is the idea, and this is how to apply the procedure to find the parameters a, b, c, etc. And then we integrate easily. Now we will move to the third case, where we have the denominator is factored out into nonlinear factors. Some of the factors are nonlinear, but not repeated. How to have the partial fraction of that kind of functions? What is the partial fraction decomposition form? This will be our next case. Now let us move to the third case. What is the third case? We have the denominator again contains irreducible factors, none of which is repeated. What do you mean by irreducible factor? You know, any polynomial, we said, we can factor it over reals into product of linear and nonlinear factors, quadratic factors. You know, if we have a quadratic expression like ax squared plus bx plus c, and we found that the discriminant p squared minus 4ac is negative, then this polynomial is not factorable over reals. If this is negative, it means the roots of this expression are non-real. So in this case, we call it prime factor. It cannot be factored out. This is the case we are discussing now. If we have, let us say, q of x is written as a product of non-linear factor, but none of them is repeated. How do we know that this is not factorable? We have this condition that says the discriminant is less than 0. So yes, this is not factorable over reals. Now, of course, this is not factorable over reals also, because always the discriminant here will be what? Less than 0. So what is the form of the partial fraction then in this case? Okay, the partial fraction decomposition form will be like this. So our function now, you remember we have p of x in the numerator, and we said this degree has a number which is less than the degree of the denominator, or the degree of the numerator is less than the degree of the denominator. The degree of the numerator is less than the degree of the denominator. So what do we have here? We have the denominator is written as ax squared plus bx plus c, where we said this is not factorable. Also, we have something like this, x squared plus d squared, for instance, and this is not factorable. What will be the form of the partial fraction? The form of the partial fraction will be like this. Look, for the quadratic expressions, always we need a linear expression upstairs. So I need what? I need ax plus b divided by a x squared plus bx plus c. Okay? So for the first quadratic factor, I need a linear factor upstairs. Okay, plus the second one now. The second one also quadratic, so it is x squared plus d squared. I need another linear one. Maybe I can call it like cx plus whatever. For example, I use the letter h, for example. So this is always possible if you have the rational function as a denominator, which is factored out into product of non-linear factors, but none of them is repeated. In this case, you need a linear factor for the first one, a linear factor for the second one. Then we can integrate the new terms. Okay. Let us look for the new shape of the fraction after decomposing. Let us, for instance, consider in this. If we have something like cx plus h divided by x squared plus d squared. Now, okay, assume we succeeded to decompose this one into such a type of fractions. Can we integrate this? And the answer is yes. This can be integrated easily because you can distribute. This will be cx over x squared plus d squared plus h over x squared plus d squared. Now, how to integrate the first one? This is a direct substitution. The question is how to integrate something like this. This is one thing. And second one, how to integrate something like that. Okay, for the first one, ax over ax squared plus bx plus c. This is not factorable. How to integrate such type of fractions? This will be discussed in details in the following exercises. So I will start first by this remark. I will prove it. And then we can use it whenever we have the case like this. What is the remark? It says if you need to integrate 1 over x squared plus a squared dx where we have a is not equal to 0. Okay, if a equal to 0, then this is straightforward to be done. Now, the answer for this is the following. 1 over x squared plus a squared dx is equal to 1 over a tangent inverse of x over a. Okay? Plus a constant, of course, plus constant c. Now, let us see how to prove this one first. And then we will use it in the next exercise. Okay. Let us start proving this result before we use it. We will use this one frequently whenever we have such type of factors in the denominator. Okay, how to start proving this? We have, this is the thing we need to calculate, 1 over x squared plus a squared dx. This is what we need to calculate. Okay, fine. What I will do, first I will take a squared common factor. I will divide by a squared. I will take it common factor from the denominator. So I have here a squared. What do we have here is x squared over a squared plus 1. So that I balance what I did. So this is dx. Fine? So I took only 1 over a squared outside. This is a squared is now taken as a common factor. Now what I will do, I will rewrite this one as this. Look, 1 over a integral of 1 over a dx divided by, I will rewrite this one as 1 plus x over a all squared. Okay, what I did here, 1 over a squared, I wrote it as 1 over a times 1 over a. That's it. And I just reorder this, x over a all squared, etc. Now, look, if you call u equal to x over a, what will be du? It will be 1 over a dx, right? So what will be the integral then? The integral will be 1 over a integral of I need 1 over a dx. This is nothing but du. All over 1 plus what? U squared. Fine. Now this is 1 over a. And what is the integral of this? It is tangent inverse of u. Now, but what is u? Of course, plus constant. Okay. What is u? It is tangent inverse u is equal to x over a. So that is x over a plus constant c. Now, this is the result we need to use whenever we have quadratic factors. And this is the proof that this result is true. That whenever we have such a fraction here, we can integrate it by using the result we are done with it now. Fine. What about the second one? Before I go to the second one, I'll give you a specific exercise about the first case. Then I go to the second one and show you how to integrate it. Okay. Let us start first explaining the partial fraction decomposition form of such type of polynomial in the denominator. So let us start with a small exercise here. Says write out the partial fraction decomposition form of the following. Now, just to combine the ideas we did, let me write something like this. X divided by something like, for example, x minus 2, x plus 2 all squared, let us say like this. And then I have here x squared plus 4, okay? The three cases we did, actually. Let's come and see. Okay, this is equal to what now? We said if this is a linear factor, not repeated, so what do we need is constant only. So constant over x minus 2. Fine. Plus. When we come to the second one, this is a linear factor, but it is repeated twice. So I need two constants. Let me call them b over x plus 2 plus another constant, I will say c divided by x plus 2 all squared. This is the first case. This is the second case. Now the third case says if you have a quadratic factor, not repeated, what will be the form? It will be a linear factor upstairs. So let us use d x plus e divided by x squared plus 4. It can be shown that this fraction here, this expression here, can be decomposed into such fractions. Now let us see how to integrate a specific exercise using the idea of partial fraction, where we have in the denominator what? Irreducible factor. If we have irreducible factor, how to do the calculation part and integrate completely the integrand. Okay, fine. Let us take a specific one. For example, I choose this. The exercise says now, evaluate the following. And we have something like integral of, okay, this is what we have here. This is x cubed plus 4x, and this is 2x squared, okay, minus x plus 4dx. Now looking for the denominator. Before we go to the denominator, let us make sure that we have proper fraction. This is of degree 2, this is of degree 3, yes. So we can start the partial fraction decomposition form after factoring, of course, the denominator. I will take x common factor, so I have x squared plus 4, and here I have 2x squared minus x plus 4 what? dx. Fine, interesting. I need to close it from here, of course. Now what do we have in the denominator? We have linear factor, not repeated. We have non-linear factor, not repeated also. What will be the form of the partial fraction? So we just write it like this. Let me just write it here. 2x squared minus x plus 4, according to the third case we did now, it says this can be written as follows. Look, for the linear factor here, what you need is a constant. So let us call it a, for example. So it is a divided by x plus. For the nonlinear factor, we need a polynomial of degree 1. We need a linear factor upstairs. So what is that? Let's call it, for example, bx plus. I usually prefer to use d instead of c, so that I can save the c for the constant of integration. So otherwise, you can use the c and use constant of integration to be another letter. It's up to you. Which letters you feel comfortable with, you can use them here. Okay. A, B, D need to be found now. Why? Because we have a rational function that cannot be integrated. We are trying to decompose it into some simpler fractions. That's our target. So how to find the parameters A, B, and D? Again and again, you multiply by the LCD. As what we did in the first case, we did in the second case, we will do in the third case. So I multiply by the LCD to get 2x squared minus x plus 4 is equal to. I multiply by the LCD to get the following. I get here a. Okay, x will cancel with x, so a times x squared plus 4 plus, if you multiply the second one, x squared plus 4 will cancel with x squared plus 4. So what you get is just bx plus d times x. So I will write it as bx squared plus dx. I multiplied by the LCD in this step. Fine. Now I have the freedom to move. Either I substitute points or I compare coefficients. I myself prefer to compare coefficients whenever we have non-linear factors. If I have linear factors, then I substitute points, it will be easier. But if I have non-linear factors, it is up to you, but I recommend you to compare coefficients. Let us compare coefficients here. What is the coefficient? What is the coefficient, for example, of x squared? What is the coefficient of x squared? What is the coefficient of x squared? Here it will be a, so it is a plus what? Plus b. And what is the coefficient of x squared here? It's equal to what? It's equal to 2. That's one thing. Now let's go to the coefficient of x. Now what is the coefficient of x? This has nothing to do with x, right? Here, x squared. So the only coefficient is d, coefficient of x. And d, the coefficient of x here is minus 1. So that is minus 1. So we get the parameter d at least now. Now, what is the coefficient or the constant term? What is the constant term? Let us say constant term. What is the constant term here? The constant, we have 4a, constant term, 4a. And then we have no constant term here. So 4a is supposed to be equal to the constant term here, which is equal to 4. So directly this implies a will be equal to 1. And if a equal to 1, you can come here and get b. A equal to 1, so b equal to 2 minus 1. So this implies also b is equal to 1. Now we get the parameters. Let us see how to integrate after decomposing. Okay, let us see how to integrate now. So we substitute now for a, b, and d. So our integral, if you allow me, I will call this one I, our integral here, not to copy it again. Our integral I will be equal to the integral of, look, this is the left hand side is equal to the right hand side. We will substitute for the values of a, b, and d. So what is the value of a? The value of a is 1. So what we have here is just 1 over x. Plus, now what I will do here, I will split this one into 2 parts. So b equal to 1. So what do we have is just x over what? X over x squared plus 4 plus d. d is minus 1. So it is minus 1 all over what? X squared plus 4. And this is something to be integrated with respect to x. Fine. This is the form of the fraction after decomposing, after making the partial fraction. So we have a single fraction here. Here we have 3 fractions, but comparing the left-hand side with the right-hand side, the right-hand side is much easier to be integrated. Now, what is the integral of the first one here? That is straightforward. It is ln of absolute value of x. Plus, let's come to the second one here. In order to integrate, I need the derivative of this. What is the derivative of this? 2x. I have x here, so I can multiply by 2 and divide by 2. So that will be 1/2, and then if you do a substitution, this will be ln of x squared plus 4. Okay? Now, come to the last one. The last one is one application for the formula we derived. Let me write the formula in front of you. If we need to integrate 1 over x squared plus a squared dx, then this is 1 over a tangent inverse of x over a. Okay, fine, plus constant c. So what is the integral of this? Our a here is equal to 2. We have 4, which is 2 squared. So a is equal to 2. Fine. Applying this formula we have, it's 1 over 2 tangent inverse of x over what? Over 2. Of course, at the end, you need to add plus constant of integration. So this shows how to calculate or how to integrate functions if it has quadratic factors, non-repeated. Quadratic factors, but not repeated. But this is one type of quadratic factors. There is another one. There is another one where we have what? Where we have 3 terms. We have something like p of x divided by a x squared plus bx plus c. Now what we did, if b is equal to 0, we know how to integrate by using the formula. Assume here we have b squared minus 4ac is less than 0 and b is not equal to 0. So this term is also appearing. The question is how to integrate this, because we need it in the partial fraction. That will be explained in the following exercise. Now let us see how to integrate if we have function like this, p of x over a x squared, as we said, bx plus c, where this is quadratic and not reducible, where the discriminant here, as we said, is less than 0. This example here will show us how to do this completely. Okay, what is the idea then here? Look for this nice exercise. Before we start the partial fraction, we need to observe that the degrees are the same. So what should we do? As we suggested before, we need to do the long division. So we need to simplify first, in other words. So I have 4x squared minus 3x plus 2. Okay? Now, I divide by 4x squared minus 4x plus 3. If we divide 4x squared by 4x squared, we get 1. 1 by 4x squared, that is 4x squared. Fine. 1 by minus 4x, that is minus 4x. 1 by 3, that is equal to plus 3. Good. Now this is minus, plus, minus. Adding, this will be 0. 3 minus 3x plus 4x, that is just x. And finally, I have 2 minus 3, that is equal to minus 1. So what's going on here? We have 4x squared, okay, minus 3x plus 2 divided by whatever we have, 4x squared minus 4x plus 3. This is nothing but equal to the quotient, which is 1, plus the remainder, which is x minus 1 divided by the divisor, which is 4x squared minus 4x plus 3. Okay, fine, interesting. So in order to integrate the left-hand side, I need to integrate the right-hand side. Fine. But this is easy to be integrated, but this one, how to integrate such a type of functions. So let me just call our integral I, and this is equal to, as you can see here, it is the integral of 1 dx, I will distribute, plus the integral of what? X minus 1 all over 4x squared minus 4x plus 3 dx. Now let's call this, of course this is clear, this is x. I will call this one I1. I call this one I2. All the integral here, I call it I2. The first one, I call it I1. I'm considering the second one. Of course, this one is so simple. This is just x. But the important part is here, how to integrate this. So I concentrate in the second one now. Consider the second one. Then we combine them together to get the final answer. I2 is equal to the integral of x minus 1 all over, this is 4x squared minus 4x plus 3 dx. Now, maybe someone would say, how do you classify this as it is quadratic, non-repeated, and irreducible? Maybe this is factorable. Now, we'll answer this by evaluating the discriminant. So, we need to find the discriminant. What is the discriminant of this? What is the discriminant of 4x squared minus 4x plus 3? Okay, we have b is equal to minus 4. We have a is equal to 4. And we have c equal to 3. So, if you calculate b squared minus 4ac, what do you get? b squared will be 16 minus 4 times a, that is 4 times c, which is 3. Clearly, this is less than 0. 4 by 4 is 16, by 3 is 48, 16 minus 48 is minus 32, so this is less than 0. So this is not factorable. Okay, so what should we do if it is not factorable? What should we do in order to solve this problem? Because we may encounter a rational function whose denominator is factored out into something like this. Okay, fine, interesting. What should we do is simple. This is what we will do. You just take the integral I2, and what you need to do is just try to rewrite it in another form. So, for example, 4x squared, I will write it like this. 2x all squared minus 4x, okay, plus 3. What you need to do is just to take this expression here, 2x all squared minus 4x, and try to add something here so that this will be a perfect square. Now, what is the term should be added here? What is the term should be added here? Now, it's very simple. You know this, a plus b all squared to be what? A squared plus 2ab plus b squared. In order to get what is the thing that we need to add, which is this, I need to divide by what? 2 and a. The coefficient of this, I need to divide it by 2a. So what I will do here, I will come to the coefficient of x, I will divide it by 2, and I will divide it by a here, which is 2 also. So what do we have here? The coefficient here. So what do we have here is the following. In order to complete the square, I take the 4, divide it by 2 in the formula, then I will divide it by the coefficient of x here, which is also 2. So that's equal to what? That's equal to 1. So what I will do, I will add 1 and subtract 1. So what do we get here? Let's come back and see. This is the integral of x minus 1 all over. Okay, this is 2x all squared minus 4x. I need to add 1 and subtract 1. So 3 minus 1 will be plus what? Plus 2, right? Plus 2. And that is dx. So actually we just use the 3 to write it as 1 and 2. Or we are adding 1 and subtracting 1. So this is exactly what we have. We are adding 1 to this expression. So it will be plus 1. And we have 3 minus 1. That's equal to 2. Fine. What is now the first term? We have x minus 1. Look, this is very interesting exercise. This is 2x plus 1 now. All what? Squared, then we have plus 2 dx. Almost done. What do we need now to do? We need to make some kind of substitution. So I need to write this one as u squared plus a squared. So I will let u to be equal to 2x minus 1. Okay? So what will be du? Du will be 2 dx. Okay? Not only this, and this implies x is equal to u plus 1 divided by 2. You solve for x only. Take 1 to the other side, so you have u plus 1. Divide by 2, you have u plus 1 divided by 2. Fine. Let us now substitute back and see what will be the new form of the integral. Let's come here. This is equal to the integral I2 is equal to the integral of, now, what is x minus 1? This is x, so x minus 1 will be u plus 1 divided by 2 minus 1. Okay, interesting. Over. That will be u squared plus 2. And what is dx? Dx is du over 2. So that will be 1/2 somewhere here. And this is what? du. Fine. Let us simplify more. Look for the integral we have. 1/2 times the integral of. This is u over 2 plus 1 half. Plus 1 half minus 1, that is minus 1 half. So it is u over 2 minus 1 half, all divided by u squared plus 2 du. Okay, interesting. Now let us split this one into two integrals. The first integral will be, I'm taking this term over this, so what do we have is 1 over 4 integral of u divided by u squared plus 2 du minus, we have 1 half times 1 half again, so it is 1 over 4 times the integral of, look, du over u squared plus 2. Now, each one of these is simple to be integrated. What do we need here is the derivative of this, and the derivative is 2u. So I need to multiply by 2, divide by 2, so this will give me 1 over 8 ln of whatever we have here, u squared plus 2. Okay? And the last one here we have minus 1 over 4. Now we apply the formula, we have u squared plus a squared, so a equal to radical 2. So what do we have? According to the formula we have, it is 1 over radical 2 tangent inverse of x over a, u over a, so it is u over root of 2 plus constant of integration. What it remains now is just to bring back what is u, substitute here to get the final answer. So the final answer will be equal to 1 over 8 ln of, what is u squared plus 2? This is u squared plus 2, which is actually our original expression. So that is nothing but whatever we have here, which is 4x squared, okay, minus 4x plus 3. That's exactly what we have. And then we have here minus 1 over, of course you can simplify this by rationalizing, multiplying by radical 2. So if you like to do that, this will be radical 2 and this will be 2. So this will be radical of 8 divided by 8. And then I have tangent inverse of, what is u? u is 2x minus 1. So that is 2x minus 1 divided by radical 2 all plus constant of integration. You may leave it like this. We may simplify more if we like to rationalize also the second term. That will be exactly what we have in the idea of integrating prime factors here, quadratic factors. But the question is not yet finished because that is only I2 and we have I1 is equal to x. Let me just finish this exercise by writing the final answer here. So this is what we are trying to find. The answer for this will be equal to, this is equal to what? This is equal to I1 plus I2, where I1 is equal to x and I2, I will say I2 is exactly what we have here. And that is the end of the case number 3, where we can integrate now any rational function if it has quadratic factors non-repeated with the two types. Maybe ax squared plus bx plus c has the b equal to 0, so we have a formula for this. If b is not equal to 0, then we need to go through the process of completing the square and get the answer. What is remaining in the partial fraction is what happened if we have quadratic factors, but some of them are repeated. That will be done in the case number 4. Now let us see the fourth case we have for the partial fraction. The fourth case we have is this. It says if the denominator q of x contains a repeated irreducible factor. If we have one factor which is of second order, that is a prime factor, and at the same time it is repeated, what will be the form of the partial fraction? So this is our assumption now. We have the function, the rational function, to be p of x over this. For sure, we are making the test that the degree of p of x is less than k in this case, or less than 2k. So the degree of the numerator is less than the degree of the denominator. This is always our assumption. Now, what is the form of the partial fraction if we have such a shape we have here? So it will be p of x divided by this, which is ax squared. We are assuming now this quadratic factor, which is ax squared plus bx plus c, is not reducible. So this cannot be factored out into two linear factors. Okay, so what will be the shape of the partial fraction now? You remember when we talked about the repetition of the linear factors, we said If we have linear factor and repeated k times, then we need k constants. Here we have a quadratic function repeated k times. What do we need? Simply we need k polynomials of degree 1 in the enumerators. Meaning, I will start, for example, say a1 x plus b1. That's the first one. Divided by, we start with ax squared plus bx plus c raised to the power 1. Then, plus, we need now another polynomial of degree 1. So we will say a2x plus b2 divided by ax squared plus bx plus c all squared. We do the same until we reach what? We need to reach the last one here is akx plus bk, p sub k, divided by ax squared plus bx plus c all to the power k. So we start with the first polynomial and the power 1, then we start increasing the power until we reach what? We reach the k repetition we have here. So if you count, we have from 1 to k, so that is k polynomials of degree 1. So let us see now if we have a rational function whose denominator involving some repetition of a quadratic factor, not factorable, what will be the form of the partial fraction? Now what I will do in the following exercise, I will summarize all cases we did. All cases we did. What are the cases we have? We have linear factors distinct. We have linear factors repeated. We have quadratic factor irreducible, not repeated. We have quadratic factor and repeated. So this question says only write out the partial fraction or the form, only the form, do not calculate, only the form of the partial fraction okay, partial fraction decomposition of the following function, or of the function we have here, it is given by the following, of the following function. And here the function we have, f of x is given to be equal to, so no need for this, f of x is equal to, let us say it is given by this, x cubed plus x squared plus 1. It is divided by, okay, I have here x minus 1, I have here x plus 1 all squared, I have x squared plus x plus 1, and I have at the end x squared plus 1 all to the power 3. Let us see how to write the partial fraction form of this. Now look for the denominator. We have linear factor not repeated. We have linear factor repeated. We have a quadratic factor not repeated. We have quadratic factor and repeated. What will be the form of the partial fraction? Okay. So I will say f of x, according to the discussion we made in this part of the material, we have the partial fraction decomposition forms. We said for the first one, for the linear factor, I need constants. So I call it, for example, a over x minus 1. A second one, plus. For the second one, this is a linear factor repeated 2 times. I need 2 constants. I call them, for example, b over, of course, the first one is x plus 1. Next, I have another constant c over x plus 1 all squared. Done with the second factor. For the third factor, I have plus, I'm talking about x squared plus x plus 1. I need a linear polynomial. So I need, for example, here I can call it dx plus e. Okay? dx plus e divided by x squared plus x plus 1, because this is not reducible polynomial. Okay, coming to the point we are discussing now. We have a quadratic factor, x squared plus 1, that is not factorable. And it is repeated 3 times. Repeated 3 times. So what should we do? We need 3 constants, 3 polynomials degree 1. Meaning, for example, I can use, for example, if you like, h 1x plus any other letter. For example, f1, this is one polynomial. It is divided by x squared plus 1. We start with the power 1. Then we move to the second one, so the second polynomial. So I call it h2x plus f2 divided by x squared plus 1, all squared until we reach the 3 here. So plus, the last one will be plus, this is x squared plus 1, all cubed. I need another polynomial here, so it is h3x plus f of 3, or f3, f sub 3. So, yes, this polynomial, this rational function can be decomposed into 1, 2, 3, 4, 5, 6, 7 sub-fractions. This is how to rewrite a function in the partial fraction decomposition. How to use this idea to evaluate the integral. That will be our next example. And the example here simply says, evaluate the following. Evaluate the integral of, and it's written in factored form like x times x squared plus 1, all squared. What we have here is 1 minus x plus 2 x squared minus x cubed dx. Let us see how to integrate a rational function involving a quadratic factor and repeated. This is the idea of the exercise. So what should we do? Before we start, as usual, we check the power here is 3. The power here is 4 times 1. So 4 plus 1, sorry, that will be 5. So the degree of the denominator is a polynomial of degree 5. Yes, we can directly apply the partial fraction decomposition forms. So what should we do now? We come to the function 1 minus x plus 2 x squared minus x cubed divided by x times x squared plus 1, all squared, and we need to rewrite it as what? For x, it is linear, so we need constant. So I call it a divided by x plus. This is quadratic repeated, so I need two polynomial of degree 1. So I have bx, for example, plus d. I will save the letter c for the constant of integration. So it is bx plus d divided by x squared plus 1 plus the last one now. This is x squared plus 1 all squared. I need another one here. So maybe I call it like ex plus whatever, h for example. Okay? So we need another polynomial divided by x squared plus 1 all squared. So this is the first step, which is rewriting the function in terms of the partial fractions. Okay, how to get the parameter a, b, d, e, and h. That's our next one, our next step. What should we do? As what we did before, we multiply by the LCD to get the following. I get 1 minus x plus 2 x squared minus x cubed equal to. If you multiply this expression in the right hand side, you get the following. Get a times, it is x squared plus 1 all squared. I simplify, I will write it as x to the 4 plus 2 x squared plus 1. That is x squared plus 1 all squared. Of course, x will be cancelled with x. Now when we come to the second one, the second term multiplied by this, look, x squared plus 1 will be deleted with one of these x squared plus 1. So what do we have is b x squared plus dx, all of this multiplied by x squared plus 1. Why is that? Because one of them will be removed. So I have x squared plus 1. This is x squared plus 1. And I have x times bx plus d. So that is bx squared plus dx. Finally, I have the last term plus. Coming to the last one, x squared plus 1 all squared will be cancelled with this. So it is just multiplying by x. That will give me what? Plus, let me write it here. E x squared plus hx. Okay? That is the multiplication of the equation by the LCD, by the least common denominator we have here. Okay, interesting. The next one, how to get the parameter a, b, etc. How to get them? I prefer, if I am doing a question like this and I have quadratic factors, to compare the coefficients of the polynomials. Meaning, I have an equation that involves polynomial to the left-hand side and another polynomial to the right-hand side. These are equal, meaning they should be equal in the degree and they should be equal in the corresponding coefficients. So what should we do now? I compare coefficients. So what is the coefficient, for example, of the coefficient of x to the power 4, for instance? What is it equal to? Look for the right-hand side. I have here a times x to the 4. So that is a is the coefficient. What else? I have x squared times x squared will give me x to the 4. So that is a plus what? B. Why? Because it is b times 1. Nothing else will give me x to the power 4 because this will give me x squared, this will give me x cubed, this will give me x. Nothing with x to the power 4. So what is the coefficient of x to the power 4? It is a plus b in the right-hand side. What about the left-hand side? It is equal to what? 0. So this is one equation we get. Second one. Let's move to the coefficient of x cubed, for example. Now, the first term involving nothing about x cubed doesn't give us anything about x cubed because no term will give me x cubed. For the second one, I have bx squared times x squared. This is x to the 4. This is x squared. Then this one will give me x cubed. dx by x squared. So it is d. Anything else? No, because this is just x. This is x squared. This is x. So it is only d. Now, what is the value of d? It is the coefficient of x cubed. That is equal to what? Minus 1. The second equation directly gives us the parameter d. What is next? Coefficient of x squared. What is the coefficient of x squared? Okay, coefficient of x squared, clearly here I have 2a. That is 2a plus. Next one. Which one will give me x squared? X squared by constant? X by x, nothing would you have here, or constant by x squared. I have b times 1, so that is 2a plus what? b. Second one. Last one, coefficient of x squared, so it's plus e equal to. What is the coefficient of x squared here? It's equal to 2. So I write 2 here. This is coefficient of x squared. Next, the coefficient of x. What is the coefficient of x? Okay, first term will give me nothing with x. This is x to the power 4. This is x squared. This is x cubed. Yes, this will give me x. d times 1. So it is d. And I have h here. So d plus h is equal to. Now what is the coefficient of x here? Minus 1. So this is equal to what? Minus 1. Good. Last one. Constant term. What is the constant term? Constant term. Okay. What is the constant term? If you go here, you just have a by 1. That is constant. A. What else? This has no constant, no constant, no constant, no constant, no constant, no constant term. So it is only a. So a is equal to what? A equal to the constant term here, which is equal to what? Which is equal to 1. You see we have 4 equations, 5 equations. 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5 unknowns. We can easily find them. These are simple equations. Let us see here. You get the value of d directly, which is equal to minus 1. Last one will give you directly a is equal to what? Equal to 1. So we can come here and substitute for a by 1, we get the value of b. We substitute for a and b, we get the value of e. We have the value of d from this equation, we get the value of h. So let us do this calculation and see what will be gained for the other parameters. Okay? Let me just make some space here so we can continue integrating also the function. So let us calculate now the other parameters. Look, let's look for the last one, a equal to 1. So from the first equation, what do we have? We have b is equal to what? I'm talking about this equation now. A plus b equal to 0. So b equal to what? B equal to minus a. Okay, so b equal to minus a, but a is already done. A is equal to 1. So b equal to what? b equal to minus 1. Okay? So we have b is equal to minus 1. That's what we have. Good. We go back to the coefficient of x squared now. I can get the value of e from here. I have 2a plus b equal to e plus e equal to 2. So what is e then? The parameter is equal to, if you convert it, then we have 2 minus 2a minus what? Minus b. Okay? So substituting now for a and b, what do you get? We will get 2 minus 2a, a equal to 1, so minus 2a will be minus 2, minus b, b is minus 1, minus minus 1, that is plus 1, so the final answer is equal to 1. 2 minus 2 is 0, so we have e now is equal to 1. Okay, now we have a, we have b, we have e, already also we had d, so we can find from here, we can get h. Now if d equal to minus 1, h will be equal to what? Equal to 0. So we have d is equal to minus 1. This one implies that e must be 0. Okay, now we have everything we need. We have a, we have b, we have e, d, etc. How to integrate now after rewriting the function in terms of the partial fraction. Going back to the integral now, let me call it I is equal to the integral of. I will call this integral, I will call it I. This integral is I. Now, integrating the left-hand side is the same as integrating the right-hand side. So what I will do, I will substitute for these parameters now. I have a equal to 1. So that will give me 1 over x. Okay? This is what we have. I'm substituting here. A over x. Now, b equal to minus 1. So that will give me what? That will give me minus, okay? It's like this, plus, then you substitute for the parameters. It is minus x minus 1. Minus x, that is b equal to minus 1. So it is minus x. D is also minus 1, so it is minus 1. Divided by x squared plus 1. Okay? Next. I have ex plus h. Okay, h is equal to what? H is, sorry, this is not e. Sorry for this. This is what? This is missed typo here. It is h equal to 0, not e. E is equal to 1. Cannot be 1 and 0 at the same time. This is h equal to what? 0. We get it from here, actually. If we substitute d minus 1 will cancel with minus 1. We have h equal to what? Equal to 0. That's fine. Now let us substitute for e. E is equal to 1. So e equal to 1. So what do we have here is just x over x squared plus 1 all squared, and we need to integrate this with respect to x. Interesting. Let us come and simplify before we integrate. So what do we have here is just the integral of 1 over x. Then I have minus. It is x over x squared plus 1 minus 1 over x squared plus 1 plus x over x squared plus 1 all to the power 2 dx. Okay, let's integrate now. This last step will be the following. I just write it like this. So equal to the 1 over x, it is ln of, don't forget, it's absolute value of x. Don't forget this. Ln of absolute value of x. Minus. Now how to integrate the second term? You just make this is equal to u. So 2x will be du. So that is minus 1/2 ln of x squared plus 1. Okay? It's supposed to be absolute value, but this is always positive, so no need for absolute value. Next one. This is clearly tangent inverse of x. Okay? Last one. What do we have here is x squared plus 1. If you make a substitution, again you need here what? 2x. And then you integrate directly x squared plus 1 to the power minus 2. It's x squared plus 1 to the power minus 1 over minus 1. So that is minus what? 1/2 times 1 over x squared plus 1. Okay? That's exactly what we have for this expression. Of course, we need to add at the end plus a constant of integration. And this example concludes the 4 cases we have for partial fraction. We have linear not repeated, we have linear repeated, we have nonlinear and non-repeated, and we have nonlinear and repeated. The next part will be, we have an application for the partial fraction in some different types of integrals. We will present some of these integrals in the following part. Now, other types of integrals. Let us see one specific type here. When we have radicals involved in the integrand, one recommendation to be used here is to let u equal to the radical there. So it is radical of x plus 4. Okay, try to rationalize this. Try to take rid of the radicals. So what do we have here? If we let u equal to, radical x plus 4, then we have u squared is equal to x plus 4, okay? And this implies what? 2u du is equal to what? Equal to dx. Now what happened to the integrand after substituting? Let us do that. We have our integral is I equal to the integral of radical x plus 4. Radical x plus 4 is equal to u. So we have here u divided by, now what is x? X is u squared minus 4. So this is u squared minus 4. And what is dx? Dx is, this is multiplied by 2u du. Okay, interesting. Now let us simplify before we integrate. So this became now an interesting, easy question here. We have 2. I will take it outside the integral sign. Then I have u squared in the numerator. This is u squared. And in the denominator, I have u squared minus 4 du. Okay, let us use the ideas now for partial fraction. Before we go, this is the same degree. So we need to simplify first. We need to divide first. If we divide, or simply we need to add minus 4 plus 4. What do we get here? 2. U squared minus 4 over u squared minus 4, that will be just 1. Plus, what do we have here is 4 over what? U squared minus 4 du. Okay, interesting. This is what we have, like this. Now, let's come to the integrand now. The first one is easy to be integrated. What about the second one? It's also easy to be integrated because this is one case of the partial fraction we did. Okay, what I will do here, I will just do it in the margin, then I will borrow my solution. I have 4 divided by u squared minus 4, that is u minus 2 times u plus 2, okay? I need this one to be constant over u minus 2 according to the discussion we made. And we have here another constant b divided by u plus 2. Multiplying by the LCD, we get 4 equal to what? A by u plus 2 plus b times u minus 2. Okay, this is linear type of the partial fraction. I mean, linear factor is non-repeated. So we said that time we need to substitute points easier. So if we substitute 2 equal to 2, what do we get here? This will be 0. This will be 2 plus 2, 4. 4 over 4 is 1. So that will give me a equal to 1. If I substitute u equal to minus 2, I will get this is 0 and this is minus 4. So b is equal to minus 1. That's what we will get. Okay? This is what do we have. Now let us borrow this and write it down here. It is 2 times the integral of 1. All of this now will be rewritten into partial fraction decomposition form as a over u minus 2 plus b over u plus 2. Substituting, that will give me plus. It is 1 over u minus 2. Okay? Then I have minus 1 over u plus 2. And this is du, and this is exactly what we have. Fine. Integrating, we get the answer to be 2 times this. U plus, if you allow me, I will write this one as ln absolute value of u minus 2 minus ln absolute value of u plus 2, or it is ln of absolute value of u minus 2 over u plus 2. All of this plus constant of integration. Maybe from here someone can use a formula to integrate or to get the value here. We derive a formula for this, so you can use it also to get the integral. To get the integral here. Okay. Now what should we do in the last step? In the last step, we need to substitute back for the value of u. U is equal to what? Radical x plus 4. The only thing we come here to write the final answer to be, this is equal to 2 times, what is u? U is radical x plus 4, so this is x plus 4. Then plus the logarithmic function absolute value of, we have u which is radical x plus 4, this is x plus 4, okay, minus 2 divided by radical of x plus 4 plus 2, all of this plus constant of integration c, plus constant of integration. That is one type of integrals, can be done by the substitution we made here, by the recombination here. I will give you another one. Let's call this one part B, and says evaluate. This question says you need to evaluate this. It is 1 over, let us say 1 over radical x minus cubic root of x dx. Okay? How to solve this kind of radical function integral? I mean integral involving some radicals in the integrand. Again, one idea here is to rationalize this, to remove the radicals. What is the substitution that will remove the radical? You just let u equal to. Now, look for the two indices here. We have 1/2, we have 1/3. What is the common denominator here? 6. So what do we have? We can take this one to be the 6th root of x. This is one way. Or you say directly what? I will let x equal to u to the power 6. It's up to you. You start this way and so on. For example, if this is a 3 and this is 4, I will take u to be the square, the 12th root of x. The index will be 12 and so on. Okay, what will happen now? X will be u to the power 6. What is dx? Dx will be 6 u to the power 5 du. Let us see what will happen now if we substitute for u by this quantity here. Okay, the integral will be the integral of, yes. I come to dx. Dx is, this is 6u to the power 5. This is du. Okay? And then I have radical x. Radical x will give me u cubed minus square root, this is square root of x. Square root of x is u cubed, and cubic root of x is u squared. I'm talking about here square root, cubic root, etc. Okay, divide by u squared up and down. What do you have is this. 6 times the integral of, I will have here u cubed over what? If you take u squared, this will be u minus 1 du. Interesting. How to integrate the new form of the integral? Be careful. Always remember that if we have the degree of the numerator is greater than the degree of the denominator, which is 1, in that case, what we need to do is to use simplification stuff. I need to use either long division or, in this case, scientific division. It's up to you. Okay, let us use the long division since you are familiar with this. So I will write here u cubed. I will write here u minus 1. If you divide, you get u squared. If you multiply, you get u cubed minus u squared. Changing the signs and adding, you get here u squared. Still, you can divide. U squared divide by u, that will give me plus u. U by u, this will be u squared minus u. Okay, minus plus. So this is u. Again, you can divide. So this is plus 1. 1 times u is u minus 1. Adding, we have 1. So you can rewrite the integrand to be 6 times the integral of the quotient, which is u squared plus u plus 1, plus the remainder 1 over u minus 1. The divisor is u minus 1, and this is supposed to be integrated with respect to u. So what is the final answer then? In terms of u, this will be 6 times all of this. U cubed over 3 plus u squared over 2 plus u plus ln of absolute value u minus 1, all of this plus constant of integration. Now what should we do at the end? We take back u and substitute. We take back u and substitute, so this will give me the following. I keep the 6 outside, or I can multiply 6 over 3 will be 2, so this will be 2 u cubed. What is u? U is equal to this. When you cube it, what do you have? You have x to the power 1 over 6 all cubed. That is only what? That is radical of, because it will be 3 over 6, 1 over 2, that is radical of x, plus, what is 6 over 2? That is 3. What is u squared? U squared will be cubic root of x, cubic root of x, okay? And then I have plus 6u, that is 6 times cube, 6th root of x, that is u. And finally I have plus, this is logarithm of absolute value of course I substitute back for u by the 6th root of x, and I have what? I have minus 1 inside here, all of this, as we said, plus constant of integration. This is the first type of integrals where we can use a specific substitution to simplify and then integrate. There is another one interesting, which is if we need to integrate a function that involves sine and cosine, which cannot be done by the classical way we did before for the trig functions. There is a specific substitution, okay? We call it the substitution tangent x over 2. How to transfer a function involving sine cosine into a polynomial over polynomial function, into rational function. That will be done in the next part. Now let us see this kind of problems. We have an integral of function that involves sine and cosine. How to integrate, how to transfer this one from a function involving sine cosine into a function of rational type. Okay, so that will be done through this specific substitution. We usually let here t to be tangent x over 2, and we choose x to be between minus pi and pi. Why? Because if you have x between minus pi and pi, then x over 2 will be between minus pi over 2 and pi over 2. So this function is 1 to 1. So we can talk about the inverse. That's one point. Now what do we need to replace here? We need to replace dx. We need to replace sine of x. We need to replace cosine of x. How to do that? Let us come to dx first. What I will do here, I solve for x. So x over 2 equal to tangent inverse of t, and this is well defined because we are choosing this specific location here. Okay, fine. So what is x then? X will be 2 times tangent inverse of what? T. Fine. So what is dx then? What is dx? dx will be 2 over 1 plus t squared dt. This is the first thing we need to replace in the integrand. Okay, that's dx. So we get a formula for dx. Now what about sine x, cosine x? Okay, fine. Let's come to whatever we have and try to establish the other things we need. Now let us call this one what? X over 2. X over 2, the argument here. Tangent x over 2 is equal to t. So this one is t, and this is equal to 1, and this is radical of 1 plus what? T squared, using the Pythagorean law. Fine. What we need to do is to get the sine of x equal to what? Okay. Sine of x. Sine of x. Fine. But we don't have something about x. We have something about what? X over 2. The information given here is about the argument x over 2. But what is the relationship between them? You can easily see that you can rewrite x as what? Twice x over 2. Then it is simply, we need to use the double angle identity for the sine. So this is 2 sine of x over 2 multiplied by cosine of x over 2. Okay, interesting. Borrow these values from the triangle, then you get the answer. It's 2 times, what is sine x over 2? Opposite over hypotenuse. So it is t over radical 1 plus t squared times cosine is 1 over radical 1 plus t squared. Good. Simplifying it, sine of x is equal to 2 times t divided by 1 plus t squared. So using this substitution, I can replace the sine of x to be 2t over 1 plus t squared. Finally, let's come to the cosine of x. What is cosine of x? What is cosine of x? Cosine of x is, the same metric will be used here. It's cosine 2 times x over 2. Okay? So what is cosine 2 times x over 2? Using the double angle identity for cosine, it is cosine squared of x over 2 minus sine squared of x over 2. That is the very famous identity for double angle identity for cosine. Fine. Substituting now, what do you get after simplification? This is what you get. You will get 1 minus t squared over 1 plus t squared. How? It's clear here. We have cosine is 1 over this. When you square it, you get 1 over 1 plus t squared. And the sine is t squared over 1 plus t squared. Subtracting, you get 1 minus. You get 1 minus t squared over 1 plus t squared. And that's exactly what we have for cosine of x. Now, how to use this idea to solve a specific exercise that will be done in the following suggested problem here. Okay, let us write this nice exercise here. It says evaluate, to illustrate this idea. Evaluate, here we have something like this. We have 1 divided by 3 sine of x minus 4 cosine of x dx. Okay, how to integrate this? If you go back to the discussion we made about sine cosine, there is no clear substitution for this. I mean, there is no direct classical substitution for the sine cosine. This is a function that cannot be integrated directly. If we gave up and there is no clear substitution, we seek the help of t equal to tangent x over 2. So what do we need to do? We will let t equal to tangent x over 2. And then, by experience, we will memorize these formulas directly without derivation all the time. And we use them to find the answer. So if we let t equal to tangent x over 2, and specifically we are moving in this interval minus pi and pi, then we have the following. Then we have the following formulas. We have 1, 2, 3. This is what we have. We use them now to substitute. Then the integral I will be equal to the integral of, look, what is dx? 2t divided by, that is 2 divided by 1 plus t squared, that is what? dt. This is dx. Okay? dx is 2 over 1 plus t squared dt. Now what about the sine function here? We have 3 times, look, sine function is 2 times t divided by 1 plus t squared. Okay? Minus 4 times cosine. What is cosine of x? 4 times, the cosine function is 1 minus t squared over 1 plus t squared. All of this multiplied by dt. So that is the substitution. Let us try to simplify now. Now, if we simplify, what will happen now? Let us make space here so that we can write. Okay, I will multiply by 1 plus t squared up and down. So this is exactly what I will get. Okay, if you multiply upstairs, you have 2 only, right? If you multiply downstairs, you have here 3 times 2t, that is 6t. And then this will be cancelled out. You have minus 4 plus 4t squared plus 4t squared minus 4 dt. Simplifying, we get the following here. I will divide by 2, so I have here 1 I have 2t squared, I'm rearranging terms, plus 3t minus 2. I'm just simplifying this by dividing by 2. Okay, of course I need to have here what? dt. I simplify the denominator, I try to factor it out into 2t by t, and this is minus 2, we needed plus 3 here, so this is 2 times, minus 1, this is 4, minus 1 is 3, so yes, this is exactly equal to what? It is 1 over 2t minus 1 times t plus 2 dt, and now you can see now we have what? We started with a function that involves sine cosine. We end up with a function that is rational function. So we can always transfer a sine cosine integrand into what? Into rational functions. And once we reach the rational function stage, we can use partial fraction, decomposition forms, and etc. Now I will just write the answer. If you like, you can do this by yourself. You calculate this. It will be something over 2t minus 1 plus something over t plus 2. I need to have the constant here and the constant here, and then I integrate with respect to t. Okay, now I will get the constants quickly here. So this is 1/2 plus 2 is 2.5 over 2, so this is 2 over 5. Suppose you can check this calculation, and you have minus 2, this is minus 4 minus 1, so this is minus 1 over 5. You can check my calculation here if it is true or not true. Okay, fine. Let us now write the last step in this exercise, or the one before the last one. Let us now integrate whatever we get at the end here. I need the derivative of 2t minus 1, which is 2 dt. I have it here. So that is 1 over 5, the integral. This implies now our integral I is equal to, yes, it is 1 over 5. Ln of absolute value of what? 2t minus 1, 2t minus 1. Then for the other one, clearly it is minus 1 over 5 ln of absolute value of t plus 2, all plus constant of integration. Fine. You can rewrite this as 1 over 5 ln of absolute value, this divided by this. 2t minus 1 divided by t plus 2. What is t? We need to substitute for t. T is equal to what? We said we let what? We let t to be equal to tangent x over 2, right? So t is tangent x over 2. So what do we have here is 2 tangent of x over 2 minus 1 all over tangent of x over 2 plus 2 all plus constant of integration. So this is another interesting type of integrals, can be treated by partial fraction after making a specific substitution. This will completely finish the discussion of partial fraction.